going to be working with the idea of functions quite a bit. So I think the best thing to do to get started is to go ahead and define what a function is. First of all, a function basically represents, for each value of x, there's only one and uniquely one y. So one way we could say that is for each value of x, there is exactly one y value. Now there's a lot of different ways to define a function, but I think this is a nice quick way to do it. We can also talk about a function by testing a graph to see if it passes the vertical line test. So if we're given a graph of a function, let's go ahead and look at a few here. Let's say we're given a parabola. We could also be given something like a third-degree polynomial. And maybe for our last one here, we'll be given a parabola that opens on its side. If we give this the vertical line test, we can see that for each value of x, there's only one y value, meaning I never pass through more than one point at a time. So this is, yes, it's a function. Same thing here. For this value of x, there's only one y. For this value of x, there's only one y. For this value of x, there's only one y. So again, yes, this is a function as well. Now here's where I have trouble. For this value of x, I have a value of y that's positive and one that's negative. So right away, this does not pass the vertical line test because it hits more than one point. So this one is not a function. So I could look at an ordered pair and I can say, okay. You could also look at sets of ordered pairs. So if we were given ordered pairs, we could analyze the ordered pairs and then try and determine whether that is a function or not. Or we could simply just go ahead and actually graph them if you were confused about the definition of a function. So let's go ahead and look at this set of ordered pairs. Let's look at 3, 4, 4, 5, and let's say 8, 2. Now we're just going to do a real quick sketch of this. It's not going to be extremely accurate. So here's 3, 4. Here's 4, 5. And here's, let's say, 8, 2. So if you run the vertical line test, you can see that it does not pass through any point more than once. So this passes the vertical line test. And also each value of x has a unique y, meaning 3 only maps to 4. It doesn't map to any other value. 4 only maps to 5, not to any other value, and the same with 8, 2. So it passes the vertical line test, so yes, this is a function. So if you're not sure about the definition, you could always do some graphing. Let's go ahead and look at another example, some sets of ordered pairs. Let's look at 1, 5, 1, 6, let's say 2, 4, and 2, 3. Well, this one right away I noticed a couple things. 1 maps to 5, and then 1 also maps to 6. I think we're going to have some troubles here. Now if we were to graph this, 1 would map to 5 like we said, and to 6, and then we see that 2 maps to 4, and then also to 3. So 2 maps 4 and 3. So that's the problem here, is each value of x does not have a unique y. The value of x, which is 1 here, has a value of 5 and 6 for y, and you can see that it doesn't pass the vertical line test. So no, this is not a function. So when we're talking about whether something is a function or not, you can apply that definition, or you could look at a graph as well. Sometimes the graph is harder to look at, depending on what you're given, but it's always one way that we can work with this. So that's how we look at a function. Let's go ahead and talk about the notation for a function. Usually when we talk about a function, we use f of x. So we might say something like f of x equals x squared plus 2x minus 1, for instance. Well, what this means is for each occurrence of x that I have here in my function, I can replace with over here. Now a lot of people think about f of x as just being my value for y, and I can replace f of x with y. That also works. Let's go ahead and look at the definition then of f of 2. F of 2 means that everywhere that I see an x in my original function, I'm going to plug in a 2. And then I could evaluate it. So for this case, 2 squared would be 4 plus 4 minus 1 4 plus 4 is 8, minus 1 is 7. I could also look at an expression such as f of, let's say, negative 3. That means everywhere in my original function where I see an x, and I'm just putting these parentheses to represent my x, I'm going to plug in a negative 3. So for here, this means negative 3 squared. You have to have parentheses around here, so this would be a 9 minus 6 minus 1. 9 minus 6 is 3. 3 minus 1 is 2. Now I could also take this and look at this in terms of graphing. I could look at x squared plus 2x minus 1 in a graph. So you could grab your graphing calculator and hit your y equal key. And again, I have x squared plus 2x minus 1. Now we can look at this and see what the graph looks like. I think I have a mistake there. Yes, I forgot my 2x. X squared plus 2x minus 1. So let's go ahead and look at the graph. And we can see that this is a parabola, so I can change my scale a little bit here. Y min is clear down here at negative 140. That's not necessary. I could just go to negative 10 here, or whichever number you pick. And I can see here's my graph. I can see that it passes the vertical line test. And then when I'm talking about evaluating it at those different points, I think we use 2 and negative 3, I could go to second table, and then I see my values for 2 and negative 3 on here. There's 2, and there's negative 3. So let's go ahead and pop those in. And again, this comes from graphing and then looking at that table. So I can evaluate and just kind of double check my work using the graphing on your calculator as well. So for 2, up here I have a 7, and you can see for here 2 I have a 7 down here as well, and for negative 3 I have a 2, and I can see I have that here as well. So this is a nice way to check your work. Now sometimes you'll be asked to work with a function and not evaluate it at a point, but evaluate it at some other values of x. So for instance, you might be given, again, f of x is x squared plus 2x minus 1. What if I were asked to evaluate this at f of, let's say, let's do x minus 3. Now sometimes this can get a little bit complicated. What this means is everywhere that I have an x, instead of plugging in a 2 or a negative 3, I'm plugging in the entire value of x minus 3. And then from here, of course, we can simplify this by expanding, combining like terms. So for this case, x minus 3 means x minus 3 times x minus 3. I can distribute the 2 plus 2x minus 6 minus 1. And then of course we can FOIL this, first outsides and insides and last. X squared plus 3x plus 3x plus 9. And then of course we can drag all of this along and combine like terms. So I have x squared plus 3x plus 3x plus 2x is plus 8x. And then 9 minus 6 is 3, minus 1 is 2. So this looks like x squared plus 8x plus 2. So you can evaluate these at points, meaning an integer value, or I can actually evaluate these at different functions. I can input one function into another. Now when we're talking about a graph of something like a function, a lot of times we're asked to talk about the domain and the range. So let's go ahead and review domain and range quick. So remember, domain are our horizontal values, and our range are our vertical values. So vertical is up and down, and horizontal is right to left. So let's go ahead and look at a graph, and then from this graph let's determine domain and range. So from here, let's say we have a line that starts at negative 2, negative 3. So we'll just go ahead and put in this ordered pair to clarify where that point is. And this graph moves up in this direction. Okay, so the domain here, again, is the horizontal. So if we look at this x value over here on the left, we can see that our graph starts at negative 2. And then my x values keep coming this way as my graph increases. And this arrow on the end means it goes on forever toward infinity. And then I can also talk about the range. So in this case, the range are our vertical values. So we can see vertically up and down, we start at -3, which is my y value. And then it runs off toward infinity. So that's an example of talking about domain and range. I use brackets here because with the brackets, that means I actually equal -2 or -3 in this case that we do. So when we're talking about functions, a lot of times we talk about whether an equation defines y as a function of x. Is kind of one way that we can say that. And so let's go ahead and see what it means to define y as a function of x. Now sometimes when we look at this expression, we might have something like x minus y equals 7. Now when we say defines y as a function of x, basically that means can we get y equals stuff over here and it's only a single expression on the right? Well, we can see for this example, I could subtract x from both sides. I have -y equals 7 minus x. And then I could multiply through by -1. Whatever you do to one side, you do to the other. So here I'd get y equal -7 plus x. So yes, this is y can be defined as a function of only things involving x. And up here, this should say define y as a function of x. So this should say of x up here. Let's go ahead and look at another example. For this example, let's look at x squared plus 2x plus y squared equals 7. Now if I tried to solve this for y, I get y squared equals 7 minus x squared minus 2x. I'd move everything across. And then to solve for y, I'd have to take the square root of both sides. So I'd get y equal plus or minus 7 minus x squared minus 2x. Now this is solved for y equals stuff, but what we have here is we have two separate expressions. We have a positive and a negative. So no, this is not defining y as a function of x because I have two different values here on the right hand side. So we have to be kind of careful about that. You look at the expression, and with that expression, if you can simply solve for y and only have one value including only x's on the right, I can't have any y's over here on the right, then you can look at those values and define those. Now when we're talking about working with some of these functions, a lot of times you can graph them and evaluate them with your calculator, but if they involve a variable, you can't. And so you have to be a little bit careful with those kinds of values. So for example, we could look at the expression f of x equals, let's say, 2x squared minus 1 all over x squared. Now if we were asked to evaluate this at 3, that would look like f of 3. So that means everywhere that we see an x, I would go ahead and plug in a value for 3. So in the denominator we'd have this squared as well. So everywhere that there's a blank, then we would just go ahead and plug in the 3. And you have to have parentheses around the base. Order of operations, 3 squared is 9. 18 minus 1 over 9. 17 over 9. So again, plugging in and solving. Be careful when you use positive and negative values because it makes a difference whether you have the parentheses around that base or not. And you don't want to have any trouble when it comes to defining these. Now a lot of times you'll be given a graph. So we might be given the graph of this and then asked to find 3. Well, we would just go 3 over on the x and figure out what our corresponding y value is. So again, if you're given a graph, you just plug in your x value for 3 and follow the graph to see where it takes you. So let's look at an example where we would be looking at a graph to find some of these values. Now this particular question from my math lab is asking us for a lot of different pieces of information. So to get started here, I'm going to start with part A. And part A says, what is the function's domain? And I'm just reading these from right up here. Now remember, domain are our horizontal values. Well, it looks like to me horizontally, this is going to go up in the y direction, but it's also going over in the negative x direction. So this is kind of starting at negative infinity and heading off toward positive infinity in the horizontal. Part B is the function's range. So let's go ahead and look at the range. Now again, range is vertical. So if we look at this vertically, up and down, we can see that it starts right here and then goes up. Well, the y value where this is starting is at -1 and it goes off toward infinity. So there's our domain and a range. Next, we're also asked to find x-intercepts. Now when we're asked to find x-intercepts, they will either ask you to list them as an ordered pair, or they'll ask you to just enter the values. So for this example, they just want the x values, not an ordered pair, but you need to always look at those. Well, the x-intercept is right here at the origin at 0, and here's the other one at 4. So our x-intercepts here are 0 and 4. And again, I'm not listing these as ordered pairs, they're just values on the graph for x. Okay, part D. Let's see, we did the x-intercepts, the y-intercepts. Well, this is not only an x-intercept right here at the origin, it's also a y-intercept. And then the missing values indicated by the question marks. So let's go ahead and look at f of -2. So this means if I come over here and plug in -2 for x, the y value that I get back out is right here is 1, 2, 3. So f of -2 would equal 3. And then I'm also asked to find f of 2. Well, if I come over here at x equal 2, I go down 1 unit, I can see that that's equal to -1 on the y-axis. So some of these problems are asking you for a lot of detail, but it's not very hard as long as you break it down into the smaller pieces. And again, we're talking about domain, range. Make sure you remember domain is horizontal, range is vertical. We also have some application problems in here that I want to make sure that we run through. So for the first application problem that we're looking at, we're talking about the value of a car decreasing. So if you think about a car being purchased at $24,500, that's the highest it's ever going to be worth. It's going to keep decreasing, and then I guess if it turns out to be some sort of a really nice car, it'll increase again in value later in 30 or 40 years. But we're talking about the years between 0 and 6 years old. So the first thing it says, a function that describes the value of the car after x years is v of x. So v of x. Well, the most the car will ever be worth is $24,500, and then it will decrease. It's going to get lower in value by $3,300. But not just $3,300 the first year, but the first, second, third, fourth, fifth, and sixth. So what I want to use here then is the variable x to describe the number of years. So this is what would go in our first blank, as we're trying to figure out an expression that would describe the value of the car after so many years. Now this is only a function that would be good for 6 years. After 6 years it might decrease more, and then from there it could even start increasing, I guess, if the car got old enough. So this is only defined for the first 6 years. Okay, so let's go ahead and plug in part 2 to this question. So we just put in the 24,500 minus 3,300x from here. It says find and interpret v of 3. Okay, so v of 3. v of 3 means what is the value of the car after 3 years? So this expression is the value of the car in 3 years. So to figure this one out, we take 24,500 minus 3,300 times 3. So 24,500 minus 3,300 times 3. Oops. Now, if you have calculators that do only one operation at a time, be really careful about the order of operations here. And so here we'd get 14,600, and that would be the value of the car then after 3 years. So let's go ahead and interpret what that means. The value of the car after 3 years, or part B, the value of B of 3 and it represents the value of the car at the beginning of 3 years. So for our purposes, we just need to go back up to the definition of the problem. The definition of the problem said this function describes the value of the car after X years. This one is saying after, not at the beginning, but after 3 years have passed. This one is at basically after 2 years have passed at the beginning of the 3rd year. So up here we go this value of 14,600, and part A would be the one that I would choose because it's the value of the car after 3 years. So that's one of the examples that you might run into with the application problems. Now for our next application problem, it's actually pretty similar to one that we've already done in the last unit. In the last unit we looked at an investment problem where we're investing some money in an account at 9% and then we suffered a loss of, let's say, 3% in another account. This is similar to that problem, but we don't have a loss. As usual, tabling really helps here. So to get started, we have a chemist working on a flu vaccine and they need to mix a 10% solution of sodium iodine. Okay, so we have two solutions. We have a 10% solution. Now this is the same thing, but this one is stronger because it's a 60% solution. That's 60% pure sodium iodine, whereas this one's only at 10%. When they get all done, they need a 70 ml mixture. Then it says write the amount of sodium iodine in the mixture, which we'll put in down here, as a function of the number of mils in the 10%. So they want us to use X to represent this one. And then find and interpret S of 30. So we're going to do this in stages. So first of all, we have some amount of sodium iodine. Okay, and then we have some sort of a percent sodium iodine. So let's say we had a 10% solution of sodium iodine and I had 10 mils. Well, 10% of the 10 mils or 1 mil would be pure sodium iodine, and that's what we'll go over here is the amount of pure sodium iodine. So to get started here, we know we have a 10% solution and we know we have a 60% solution. And at the total, we know we need 70 mils. So this is our total. Well, it told us right up here that they want us to use X for the amount of 10% solution. So this value would be 70 minus X, because we know we need a total. So if this was 10, this would be 70 minus 10, or 60. So this is X, so this is 70 minus X. Now the amount of pure sodium iodine would be 10% of the total amount of solution. Over here this would be 60% of the total amount of solution. Now it says the amount of sodium iodine in the mixture then would be these two added together. So if I take and add these, that's what will go in this space here. So I have 10% X plus 60% of 70 minus X. And that's equal to the amount, cap S of X, that they're looking for up here. Now part 2 says interpret S of 30. Well, S of 30 basically means everywhere that I see an X, I'll plug in a 30. Okay, so 10% of 30 would be 3, and then I have plus 0.670 minus 30 is 40. Now order of operations, I have to be careful here. I do this multiplication first. 60% of 40 would be 24. So I get 24 plus 3 is 27. So what we're looking at then there is 27 mils. So our answer is 27, but it's going to ask you to interpret this value. So if we were asked to interpret this, we'd say S of 30, okay, remember X was 30, X is the amount of 10% solution. So the value of S of 30 is 27 milliliters. And what it does is it represents the amount of sodium iodine in the mixture when 30 mils of the 10% solution are used. because this is our 10% solution, because up here in our problem, they told us that x was the 10% solution. So be careful when you're filling this out to determine how to interpret that particular value that you get in the end. Now this last problem that we're going to look at is not really an application problem, but it is a little bit tricky, and it's tricky because of all the negative signs running around here. So this says find f of negative x and then subtract the original function f of x. So our original function f of x is equal to x cubed plus x plus 8. Let's go ahead and find f of negative x now as well. So this means everywhere that I see an x, I'm going to go ahead and plug in a negative x. That's what this means. It says everywhere that I see my variable x, I'm going to plug in a negative x. Now, let's go ahead and simplify f of negative x. So this would be a negative times a negative times a negative is a negative x cubed minus x plus 8. Now remember, our original problem said take f of negative x and subtract f of x. Okay, so f of negative x I just found and simplified, so that's a negative x cubed minus x plus 8. And then I need to subtract. And because I'm subtracting this entire value, you need to make sure you have up a set of parentheses. And then I just go ahead and plug in my value of f of x from up here. And then to simplify, what we need to do is take the negative and distribute. So I'd have a negative x cubed minus x plus 8 minus x cubed minus x minus 8. And then of course we can combine some like terms. I have a negative 2x cubed minus x is a minus 2x, and 8 minus 8 is 0. So my solution here is a negative 2x cubed minus 2x. Now you have to be careful when you're entering these values. You have to make sure you always put parentheses around the base, whether it's positive or negative, because that'll make a difference in your solution. As usual, if you have any questions about the lecture, please stop by my office. The Math Center is also open. You can also bring your questions to class. Good luck on this assignment.